15 minutes, so I'm not going to drag you guys too long today and let you get back onto your own work today. But I had a few questions for you. First, I wanted to say that I really like the work you've done. There's a lot of different aspects about your design and kind of your strategic vision that I'm inferring that is actually quite inspiring. So I had a few questions around a couple of things that are actually maybe a little bit of a deeper dive than, explain this, that, or the other, because you've done a very good job of explaining your work. One thing I wanted to understand is what kind of trade-off analysis did you do at a high level between your thin can airframe based design versus, say, a unibody design, which everybody else seems to use, right? First thing you do is buy the fiberglass tube, and then you figure out how to fit fins on it, right? You guys are taking it the other way around. You build a frame, put fins, put motor mounts, all that kind of stuff, and then just put some cladding on it so it's aerodynamic, right? What kind of trade-offs at a system level led you to that design point? Whether it's weight, cost, whatever. Could you kind of elaborate that a little bit for me?
Yeah, so that's a really good question. That's more of like a historical thing that we've done and an integration thing, because as you can tell, we don't do minimum diameter rockets because we want to have the diameter to accommodate a CubeSat as our payload. So in doing that, that makes our entire airframe 6 inches instead of the 4 or whatever it is for 98 millimeters. And that's just what we've done in the past is we've kept like straight body tubes and then built a frame instead of a fin can just because we had the room to do so. Also having not a continuous fin can or a continuous set of fins means we can replace one if we damage one at competition. But we haven't done any like a quantitative trade studies in terms of doing something like that. Obviously, we know that having a minimum diameter gives us a lot less drag. That's why we're doing the boat tails. So there might be something we could do in the future is to have the entire aft section of the rocket be minimum diameter. But yeah, so far it's just an integration and that's what we've done in the past type of situation.
So minimum diameter aside, yeah, obviously with a square, the frontal area is a big driver in both boat tail or tail drag and nose drag, right? But even if you were looking at like a 6-inch can that was using through wall kind of I-beam fin construction, if you will, versus this design, do you feel that there are structural advantages with going with the airframe based design, or is it an ease of manufacturing, or to your point, the ability to kind of replace parts that may get damaged? Or is it because of the capabilities of the team and kind of the shops you have availability of, to be able to do aluminum manufacturing? Is it cost? Is it cheaper to kind of do an airframe based design than to go buy a 6-inch tube and figure out how to put a boat tail on it? Any thoughts there?
Yeah, so I think you covered a lot of the aspects that went into why we haven't changed our design. We're very comfortable doing sheet metal and doing machined aluminum components. We're not super confident with our composite ability because we've really only done our fins as composite structures. We've never manufactured a nose cone or a body tube. So we kind of just wanted to stick with what we know how to do. Also, in terms of cost, we wouldn't have to develop or do a bunch of prototypes to validate the structure, especially since with the COVID restrictions, especially in Ontario, it's basically been the past 9 months where we're not allowed to have any type of in-person event. So that's been pretty difficult. So we thought that we'd just stick with our tried and tested design. But in the future, yeah, we could definitely go with something that isn't as it's probably a lot more bulky and heavy than we could actually get away with. But it is nice because we get a little bit of room inside the boat tail shroud, so we could hook up instrumentation in there. Our propulsion lead, Phil, wants to, we're going to try to do a hybrid next year. We've been working on that really hard. And that would let us have plenty of room for vibration sensors and thermocouples and other stuff like that.
That's an important piece of information I think that would be nice to include in future reports, right?
Okay.
What is your longer term kind of strategic intent or of evolution? If you think about, even if you're doing Microsoft Windows development, there is some notion of what is Windows 11 going to have, that's an improvement over Windows 10. Maybe I shouldn't be talking because maybe I'm a Linux geek. But just having a long-term vision is really helpful. It helps map for your successors, how they can follow in evolution. Let's see. I want somebody to explain to me how they've proven that 3-ring retention system, release system. Are we sure that there's enough actual pull on that to kind of release those rings? And what kind of testing was actually done on that, if any, with a loaded rocket?
Yeah, so I can talk to that a little bit.
Okay.
The 3-ring mechanism we've actually flight proven twice now, I believe. So it flew on our 2018 and 2019 rockets, both of which it did successfully deploy the main. It's just that there was an issue of when it deployed the main on those rockets. So I believe the actual plan with that was that the 3-ring would be carrying the loads itself. And then there's a drawstring on that, which you can pull, which essentially will release the entire mechanism. So we've done a ton of testing through staircases and stuff with mass simulators in order to actually prove that it will deploy. And that combined with the fact that it has been flight tested and has been proven to actually deploy our main, we are pretty confident in the design of that. And the original design for the 3-ring comes from what's used on skydivers. So typically, if you need to ditch that main parachute when you're a skydiver, you really don't want it to fail. So 3-ring in that case functions well enough to put someone's life on the line.
So that's a little feedback I would have for you as well, is that, so I've not reviewed your past projects, right? And other judges who are looking at this year's reports have probably not viewed your past projects. Some of them know about the work that you've done in the past and commend it highly. So if there has been testing that's been done on previous flights, that's actually good evidence to kind of bring forward in your reports, right? Because one of the things I'm charged with doing is saying, is this rocket safe to fly? And so I'm looking at all the details, right? That's what I do, right? In terms of what areas do I have questions about? So if you want to prevent questions, they make sure you kind of cover that next year, right?
Yep.
And it's all part of this. How do you evolve? And how do you drag along that body of knowledge with you and document your learnings and rationalize why you're making decisions that you're making this year, right? Does that make sense? Yeah.
Yep, totally makes sense. We'll be sure to add that in our future reports with direct referencing.
I want to talk about magnetometers for a minute. So do you really expect that those magnetometers to give you meaningful information with brushless DC motors in the area?
That's actually a really good. Oh, I guess Sam, you can probably speak a little bit more on that than me.
Oh, sorry, no. If I assume you mean the magnetometer.
Yeah, if it's referring to the payload, that's
sorry,
a
yeah.
pretty good point. But in terms of getting a proper reading of, sorry, let me start from the beginning there. It's meant to be a lot more of a proof of concept of the actual. I'm sorry, I started bad twice. Yeah, I think it should be able to properly work.
Can I hop in if you guys don't mind? So yeah, I realized we didn't really realize that, and that seems like an obvious thing. But I was recently watching a video about the Shinkansen, the maglev trains that they have in Japan. And they're talking about all the superconducting magnets and all the levitation magnets and stuff. And I'm like, that's a lot of magnetic fields. How do their electronics work? But they said that what they do is they just have giant magnetic shields around the passenger cabins and everything. So maybe that's something we could try to do, is shield the electronics from the whatever comes off of the DC motors.
I think a more concise answer would be it didn't really seem to be much of a problem in testing.
Yeah, I think what you'll find in testing, well, it depends on how you're testing, right? So I use the LSM1, the DS1, the 9-degree of freedom position sensor on some guided rockets that I'm building, right? I don't use the magnetometer. I use the gyros and I use the load cells, right? Because the Earth's magnetic field is phenomenally weak. And if I've got servos in the area that's dithering fins, they dwarf the magnetic fields that are generated by these proximal devices dwarf the magnetic field of the Earth that does anything in terms of like 9 degree of freedom position sensing with magnetometers. So that's where my question is coming from, right? Is like, you know, when you're thinking about using a 9 degree of freedom position sensors and stuff like that, if you're actually doing something with it, like working servos or, you know, working gimbals or anything along those lines, I suspect you're going to have some interesting kind of telemetry coming off of those magnetometers. Maybe that could be a little bit of testing that you do, is like, you know, fire it up live on the desk and then watch what happens to the magnetometers as you walk by with a, you know, a spark generator or you know, or a small servo. You know, it might be interesting work. But that's one thing that caught my eye, because I'm kind of in the space of working with IMUs as well. So that kind of caught my eye.
And just quickly, in terms of the stability control on the payload, it is affected a lot more, I think, by the gyroscope, and I think that's why I saw very limited effect from the actual magnetometer.
Yeah, that's kind of the same way I went. I just basically turned off the magnetometers because I can get all the data, the precision I need out of, you know, the G sensors and the gyroscopes. I'm trying to see if there's what else I have here. Those are the 3 questions that I had. Again, I think you're doing fantastic work. I appreciate the work that you're doing there, and yeah, I think you're going to score well. And I'm looking forward to seeing your rocket fly one of these days. Hopefully, when we get all out of crisis. It's been a really rough year for everybody, and your perseverance through all this has been remarkable. So really good work, and keep it up. You guys are doing fantastic stuff. And I look forward to seeing more of it in the future, okay?
Yeah, thank you for the kind words.
Yeah, no worries. Yeah.
Thank
Have a blessed afternoon and enjoy the rest of the conference, okay?
You too.
You too.
Okay, bye now.
Thank you very much.
Yes, thank you.
Take care.
Thank you.